Okay, so we already know that 4 points in the last video. 4 points z, z2, z1, z2, z3, z4 lie in a on a circle, lie on a circle if and only if the cross ratio z1, z2, z3, z4 is real. So we did the computation. We figured out one, it is a straight line, one, it is really a circle, right? And here, this circle means a circle in C infinity. It includes a line, a straight line. Okay, so now let's continue this line and give the next theorem. It says a Mobius transformation takes circles onto circles. Take circles onto circles. Okay, so let's see how do we prove them. Assume we have a circle, arbitrary circle. Let gamma be any circle, any circle in C infinity. So here this circle could be a straight line. And let S be any Mobius transformation. Mobius transformation. All right. You have a circle, then you can select 3 distinct points on the circle. So let Z2, Z3, Z4 be 3 distinct points on gamma. And we also know that those 3 distinct points will uniquely determine this gamma, right? We have 3 points, and we also name the images of those 3 points under S by W. Let Wj be S of Zj for j equal to 2, 3, and 4. All right. Then you have 3 different points. S is a Mobius transformation. Then you will get a circle. So 3 points will determine a circle. So W2, W3, W4. Determine a circle gamma prime. Determine a circle gamma prime. Okay, and we claim that S of gamma is equal to this gamma prime. So how do we claim it is equal to the gamma prime? So we're going to show, we will show that for any Z in gamma, its image SZ belongs to gamma prime, right? That's exactly the meaning of this. And SZ belong to gamma prime. How do we show that? Well, this is equivalent. It is equivalent to show S of Z, and then you see the gamma prime is determined by W2, W3 in W4. We're going to show this is real. It's equivalent to show this cross ratio is a real cross ratio. Correct? And, oh, okay, so let's check what this is. S of Z, W2 is S of Z2, W3 is S of Z3, W4 is S of Z4. So it's cross ratio composed with Mobius transformation of S. Okay, and we had a proposition. This is proposition 3. Okay, proposition 3.8. You can go back and check this proposition. It says this is equal to cross ratio Z2, Z3, and Z4. The cross ratio is compatible with the Mobius transformation. We actually proved this property based on the we proved this proposition based on property and the detailed computation. We did the detailed computation. So this is correct. And this one, because Z belongs to gamma, gamma is determined by Z2, Z3, Z4, and so this is real. So we're done. We proved that S of Z belong to gamma prime. S of Z belong to gamma prime, right? Okay, so that is the theorem. The theorem says if we have a circle or straight line, two cases, and then we have a Mobius transformation of S, then we still have a circle or straight line. But possibly we will map a circle to a straight line, or map a circle to circle, or we map a straight line to circle, or we map straight line to straight line. So we may have, well, this is the end of the proof. We may have 4 different situations. We may have 4 different situations. So, right? So first, remember that we have steps. First, we have the domain, and then we have the function, and then we have the image. Okay? So domain, function, and image. So that's in this order. And we still have the a circle in C infinity. All right. Well, if we change the order, for example, assume we have a circle and another circle, 2 circles, or maybe straight line, whatever. Straight line and straight line. We have them together first. We want to construct a Mobius transformation. How do we do this? Or can we do this? Okay, so can we do this? You see here, first place we have Z, Z2, Z3, Z4, and then we have S, and then we get W. Now the problem is that, so we are talking about the new situation. So now let gamma prime be 2 circles in C infinity, and let Z2, Z3, and Z4 in gamma, and W2, W3, W4 in gamma prime. Okay, so we want to construct a Mobius transformation. With S of Zj is equal to Wj, j equal to 2, 3, and 4. So we want to do this. Now we want to construct the map. Here, this theorem 3.14, we want to study the image. We are talking about different parts. Okay, how do we do that? We first, I don't know how to do this general stuff, but I know how to map this to the straight line, the real line. So we define R of Z to be Z, Z2, Z3, and Z4. Then this R of Z is from gamma to real line include infinity. Right? So R is a Mobius transformation from gamma to this extended real line, including infinity. And then we define and we define S of Z to be, no, not S, let's use T. T of Z to be Z, W2, W3, and W4. T of Z is like this. Then T of Z is from gamma prime to the extended real line. It's 1-to-1 onto. It's onto. It's onto. Okay, and then we define what? We define this S. Remember, S is from gamma to gamma prime. So we start from gamma to R and back to gamma prime, T inverse. Okay, so this is the Mobius transformation. The inverse of a Mobius transformation is a Mobius transformation. Composite of two Mobius transformations is still Mobius transformation. So this is the required Mobius transformation. This is a required Mobius transformation, right? Why it is required? Because you see here, it connects Z2 to W2, Z3 to W3, and Z4 to W4 by the definition of a cross ratio. By the definition of cross ratio, this is a 1-0 infinity. This is 1-0 infinity. And also, it guarantees that it preserves it maps circle onto the circle, right? Okay, so with this definition or with this construction in mind, we have 3.16 proposition. Okay, the proposition is just an organization of what we just discussed. For any given circles, gamma and gamma prime in C infinity, there is a Mobius transformation. There is a Mobius transformation T such that T of a gamma is equal to gamma prime. It's onto. Furthermore, we can specify that T take any 3 points on gamma onto any 3 points of gamma prime. Like this, we have Z2, Z3, Z4. We choose those 3 points, and we also choose their images, W2, W3, W4. We claim if we require this, then this T is unique with TZJ equal to WJ, J equal to 2, 3, 4, then T is unique. There's only one T with such property. Okay? The proof is already given by this construction. The existence is given. And the uniqueness is always determined by the actions of a Mobius transformation over arbitrary 3 distinct points. So the uniqueness is always determined by the actions of Mobius transformations on 3 distinct points. Whenever you have 3 distinct points, then you always have a uniqueness. Okay, so that's the circle-to-circle stuff. So a circle will be mapped to circle by the Mobius transformation. 2 circles, we can design a Mobius transformation from one to another one. Right? So circle is done, but we know that the circle, once you have a circle, it will give us, this is called the outside, the exterior. This is called the inside. If we have another circle, you may also have outside and inside. So what is the relation when we have a Mobius transformation about the outside and the inside? What can we say something? So that's the next step. We're talking about the property of outside and inside related to the Mobius transformation. To discuss this, we need a new concept. It's called the symmetry. It's called symmetry because we can see that the inside, outside, they're symmetric. What we can say they are paired with respect to a circle. Before we talk about the symmetry. All right, it's paired with respect to a circle. Okay, so first let's give the definition. The definition says let gamma be a circle through points Z2, Z3, Z4. Okay, so we have 3 points and the determined gamma. The point z and z star in C infinity, you have a pair of points are said to be symmetric with respect to gamma. If z star, z2, z3, z4 is equal to z, z2, z3, and z4 with a complex conjugation. So this is the symmetry with respect to a circle. Symmetry with respect to a circle. Before we do the further discussion about the definition, we need an observation. Actually, this definition at this moment should be examined about the well-definedness. Why? You see here, gamma is a circle. It contains infinitely many points. But you just choose z2, z3, z4. You choose 3 points. You may choose this set of 3 points. You may choose another set of 3 points. Will they always give you the relation? So for example, if W2, W3, W4 are also on the same gamma, then do we have Z star W2, W3, and W4 is equal to Z, W2, W3, and W4. Okay, well, we always have such property. Because if this is not the case, then your symmetry will be with respect to gamma and the triple Z2, Z3, Z4. Okay, so that's the important thing we should explain. This is an exercise, but I think the exercise requires a discussion. So let's see. To show this is good, let's first start from the exercise, I think that's 8. Exercise 8 says if you have a Mobius transformation from the real line to the real line, well, including infinity, extended. It's a Mobius transformation. And R of Z, no. Let's say. Let's say exercise 8. Let me copy exercise 8. Okay, so if T of Z equal to AZ plus B over CZ plus D, this is a Mobius transformation. Show that T of R infinity extended real line is equal to the extended real line if and only if we can choose A, B, C, D to be real numbers. Okay, so it basically says the Mobius transformation preserving real lines are given by the real coefficients. And first of all, these coefficients are not unique, so we can choose a group, a set, so that they are all unique. They are all real. Okay, so how do we prove this? Okay, let's check. T of R infinity is equal to R infinity. So T infinity belong to R real. Belong to R infinity, right? T infinity belong to R infinity. What is T infinity? T infinity is A plus b over infinity, c plus d over infinity. In this case, we're talking about the limit, so we are going to divide top and bottom by z, and let z approach infinity. So this is a over c. So a over c belong to R infinity. A over c belong to R infinity. A ratio of two complex numbers is R infinity, so we can choose. So here, without loss of generality, we can choose. We just say we can choose. A, C are both real. If you get infinity, you just choose C to be 0, A to be whatever real number. This is infinity. Any others, you should choose proper ones. Okay, so we can do that. This is not to say we always have this. We just say we can get this. Okay, so A and C so far is a real numbers. Now let's check T of 0. T of 0 is also belong to R infinity, right? T of no, let's choose this. T of some number, T of a real number R. T of a real number R is equal to 0 because 0 belongs to the R infinity. So T of R is equal to 0. Our ratio is 0, so we get AR plus B over CR plus D is equal to 0. So you get AR plus B equal to 0. Remember, R for some R in R infinity. Okay, so this implies what? This implies B belongs to R. B is a real number. B must be a real number. Okay, so because B is equal to negative A times R. A is a real, R is a real, so A times R is real. So B is a real number. So we get A, B, C are all real. Okay, so you see here, there's some orders. Now let's check T of 0. T of 0 belong to R infinity. What is T of 0? You let Z be 0, so you get B over D belongs to R infinity. So B is real, then it implies D belongs to R. Okay, so A, B, C, D can be chosen all in what? In R. All right, so we see that if you have a Mobius transformation preserving the real lines, then those coefficients could be all real numbers. Okay, keep this exercise in mind. Let's talk about our well-definedness of the symmetry. Assume we have Z2, Z3, Z4, W2, W3, and W4. Let's see. We show the well-definedness. We define f of z to be what? To be z, z2, z3, z4, and g of z to be z of w2, w3, w4. Remember that we are going to show we have f of z complex conjugate is equal to f of z star. This is f of z complex conjugate. This is f of z star. We want to show g of z complex conjugate is equal to g of z star. Remember, we never show f is equal to g. That's not what we want. All right. So let's check. This is F will map Z2, Z3, Z4 to 1, 0, infinity, then F inverse will map 1, 0, infinity to Z2, Z3, Z4. So F inverse will map R infinity to gamma. And G map gamma to R infinity. So if we compose G with F inverse, then it is from R infinity to R infinity. Okay, so H can be chosen with all real coefficients. Okay, if H, you see here, H AZ plus B, CZ plus D. A, B, C, D are all reals, then H of Z bar is equal to, let's see what we get, AZ bar plus B, CZ bar plus D. Then it is equal to AZ plus B, CZ plus D. Remember, A, B, C, D are all real, so we don't have the complex conjugation. And this is H of Z star, complex conjugate. Complex conjugate. Okay, so that's a property. That's a property we have. All right. Okay, now let's try to do it. Let's try to do it. So we have G compose F inverse of what? Of F of Z star. Let's check this. So G, F inverse F, they cancel. This is G of Z star. On the other hand, F of Z star, where is F of Z star? Here, F of Z star. G compose F inverse is H. It is F of Z complex conjugate, right? It is F of Z complex conjugate. By our observation, we know we can move this complex conjugation outside. So from inside to outside. So it's H of F of Z, complex conjugation. And then we write H as a G compose F inverse of F of Z. And we cancel F inverse with F. We'll get a G of Z, complex conjugate. You see, we get a G of Z star. G of Z star is equal to complex conjugate of a G of Z. So we are done the proof. So the well-definedness is verified by this process. In this process, we specifically use the property that if a Mobius transformation preserves real lines, then all the coefficients can be chosen all real numbers. Okay, so that is the important property. That is exercise 8, and this well-definedness is exercise 11. So I will suggest you to do those exercises by yourself. Again, try to understand the orders or the reasons behind those exercises. Okay, so we will stop the lecture at this moment in this video. We will continue this lecture in the next video. Okay, the lecture is not finished. Okay, thank you. We'll continue in a different video.